400 years ago, we thought Earth was the center of everything. We were wrong. 100 years ago, we believed our galaxy was the entire universe. Wrong again. 50 years ago, we were confident we understood what reality was made of. We were catastrophically wrong. Today, we're facing the most disturbing realization in scientific history. The more precise our instruments become, the more we discover how blind we actually are. 85% of reality is completely invisible to us. If you're ready to discover what we've been missing, hit that like button and subscribe. We're about to explore the universe we can't see. 1970, Arizona desert. A woman adjusts her telescope in the freezing darkness above her. Vera Rubin had 4 kids at home. She wasn't trying to revolutionize anything. She just wanted to answer one simple question. How fast do stars spin inside a galaxy? Boring, right? Sometimes the simplest questions hide the most terrifying answers. That night, she pointed her instrument at Andromeda, our neighboring galaxy, a beautiful spiral floating 1.5 million miles away in the void. Vera spent months preparing for this moment. She wanted to measure star speeds at different distances from the galactic center. Basic astronomy, routine work. Since Newton, we've known exactly how rotation works in space. The farther you are from the center, the slower you move. In our solar system, Mercury races around at 30 miles per second. Neptune, way out at the edge, crawls at just 3 miles per second. This pattern has held true for 400 years. Vera expected Andromeda to follow the same rules. The numbers appeared on her screen. She frowned. Something was catastrophically wrong. Stars at the edge of Andromeda were flying at 186 miles per second. Stars near the center, also 186 miles per second. According to every law of physics we know, this should be impossible. Vera checked her calculations. She remeasured everything. She observed other galaxies. Every single one showed the same pattern. These galaxies should be tearing themselves apart. Their stars should be flung into space like passengers on a spinning ride that's going way too fast. Yet Andromeda has existed for billions of years. Perfectly stable, perfectly intact. Only 2 explanations exist. Either every physics law we've ever discovered is fundamentally broken, or something massive is hiding inside these galaxies. Something we cannot see at all. Something invisible holding everything together with pure gravitational force. Vera Rubin just discovered that the universe is hiding something from us. But here's what makes this discovery even stranger. She had no idea how much was missing. How do you weigh something as gigantic as a galaxy? You can't exactly put it on a scale. This might sound impossible, but scientists figured out an elegant trick. Watch how this works. Imagine you want to weigh Earth without any equipment. Seems ridiculous. Actually, it's straightforward. Just observe how fast the moon orbits us. The more massive Earth is, the stronger it pulls the moon. The stronger the pull, the faster the moon travels. You can calculate Earth's mass just by watching motion. Vera Rubin used this exact method with galaxies. She observed how stars orbit around galactic centers. From their speed, she calculated the mass needed to keep them in place. The math is confirmed. The method is proven. Scientists have used this technique successfully for decades. Then came the shock. When Vera counted everything visible in Andromeda, every bright star, every dim star, every gas cloud, every speck of cosmic dust, she found only 1/5 of the necessary mass. Where were the other 4/5? Think about your house resisting wind. Now imagine calculations show your house should weigh 5 times more than it appears to keep standing. 80% of your house would be invisible. That's exactly what Vera discovered about galaxies. 80% missing, 80% unaccounted for. This wasn't a small error. This wasn't instrument malfunction. This was a fundamental problem with reality itself. Scientists call this the galaxy rotation problem. It's been confirmed in thousands of galaxies across the universe. Every single one shows the same pattern, Every single one is missing most of its mass. The invisible mass isn't randomly scattered somewhere far away. It's everywhere. It surrounds every galaxy. It fills the space between stars. Billions of invisible particles are passing through your body, through your skin, through your bones, through your brain. You don't feel anything. You can't block them. They leave no trace whatsoever. Yet this invisible substance represents 80% of everything that exists. You're living in a universe where most of reality is completely hidden from your senses. But what exactly is this invisible mass made of? Scientists needed a name for this invisible substance. They called it dark matter, not because it's black, because it doesn't emit any light at all. It doesn't absorb light. It doesn't reflect light. It's perfectly transparent to every form of electromagnetic radiation, confirmed by decades of observation. Think of it like a ghost universe overlapping with ours. Dark matter exists in the same space we occupy. It just refuses to interact with anything we can detect. The only way it touches our world is through gravity. That's it. One single force connecting two separate realities. You can't see dark matter. You can't touch it. You can't communicate with it. The only evidence of its presence is how it makes other objects move. Imagine a massive invisible hand pushing stars around galaxies. You'd never see the hand. You'd only see the stars responding to its grip. Dark matter doesn't touch anything in our visible universe, except through gravitational pull. Yet this single interaction is powerful enough to hold entire galaxies together, strong enough to structure the entire cosmos. Here's the disturbing part. The ratio isn't random. 85% invisible, 15% visible. This exact proportion is necessary for the universe to function. Change it even slightly, and everything falls apart. Galaxies wouldn't form. Stars wouldn't ignite. Planets wouldn't exist. We're like the tip of an iceberg floating on an ocean we can't perceive. Everything we see, every star, every planet, every human being, represents just 15% of reality. The other 85% exists in a realm completely beyond our senses. Some physicists compare this to living in a two-dimensional world. While a three-dimensional reality surrounds you, you'd never perceive that extra dimension. You'd only notice strange effects you couldn't fully explain. That's our situation with dark matter. But if dark matter really exists, we should be able to detect it somehow. We should be able to track it down, study it, understand what it's made of. That's when scientists launched the most extraordinary hunt in history. They decided to catch something that doesn't want to be caught, something that barely interacts with our world at all. The question became simple. How do you trap a ghost? Right now, this second, trillions of dark matter particles are passing through you, through your chair, through the floor beneath you, through the entire planet. They're moving at hundreds of miles per second. Nothing stops them. Nothing slows them down. One particle just went through your left eye, another through your heart, thousands more through your lungs as you breathe. You feel absolutely nothing. This has been happening every moment of your entire life, every moment of human history, every moment since Earth formed 4.5 billion years ago. Scientists estimate that in one single second, about 100 billion dark matter particles pass through every square inch of your body, confirmed by calculations based on the density of dark matter in our region of the galaxy. That's more particles flowing through you than there are stars in the Milky Way. Every second, non-stop, forever. These particles don't care about matter the way we understand it. A wall of solid steel is as transparent to them as empty space. The entire Earth is transparent to them. They pass through the planet's core like it doesn't exist. Imagine being able to walk through walls, through mountains, through planets. That's dark matter's reality. Here's what makes this even stranger. Dark matter particles might be passing through each other too. Right inside your body, dark matter could be intersecting, overlapping, moving in opposite directions through the same space. Think of two clouds of smoke passing through each other without mixing. That's how dark matter behaves. Some of these particles have been traveling through space for billions of years without ever hitting anything. They've crossed entire galaxies. They've passed through countless stars and planets. They've witnessed the entire history of the universe, and they've never once touched anything solid. You're living inside an invisible ocean. An ocean so vast it contains 6 times more mass than all visible matter combined. You swim through it every day. You breathe it. It flows through your DNA, yet you'll never feel even a single particle. But scientists refuse to accept invisibility as an excuse. If these particles exist, they must interact with normal matter occasionally, maybe once in a trillion collisions, maybe once in a quadrillion. That's enough. That's what scientists decided to hunt for. That incredibly rare moment when dark matter finally touches something we can detect. Building that trap would require the most sensitive instruments humanity has ever created. Before we hunt dark matter, we need to understand what makes it so impossibly difficult to catch. Dark matter breaks every rule about how matter should behave. It's matter that refuses to act like matter. First, dark matter doesn't emit light. Every normal particle we know radiates some form of energy. Electrons emit photons. Atoms emit heat. Even the coldest gas clouds in space emit faint radio waves. Dark matter? Nothing. Complete silence across the entire electromagnetic spectrum, confirmed by every telescope ever built. Second, dark matter doesn't absorb light. When light passes through normal matter, some photons get absorbed. That's how we see things. Light bounces off objects or gets swallowed by them. Dark matter lets every single photon pass through unchanged. It's perfectly transparent to light of every wavelength. From radio waves to gamma rays, nothing interacts. Third, dark matter doesn't reflect light. Shine the brightest laser in the universe at dark matter, and the beam passes straight through like shooting light through empty space. There's no surface to bounce off, no boundary to mark where dark matter begins or ends. Fourth, dark matter doesn't collide with normal matter. Almost never. The odds of a dark matter particle hitting a normal atom are astronomically small. Scientists calculate that a dark matter particle could pass through a wall of lead 1 light-year thick and probably not hit a single atom. That's a wall 6 trillion miles deep. 6 trillion miles of solid lead, still transparent to dark matter. Fifth, dark matter might not even collide with itself. Some theories suggest dark matter particles pass through each other as easily as they pass through us. Other theories propose that dark matter does interact with itself, which could explain how it clumps together. This remains theoretical. Nobody knows for sure. So, what does dark matter actually do? It pulls. That's it. Dark matter exerts gravitational force. It attracts other matter through gravity. That's the only confirmed interaction we've detected. One force. One single connection to our reality. Imagine trying to study something that refuses to emit signals, refuses to absorb signals, refuses to reflect signals, and barely touches anything physical. You're essentially trying to study something that doesn't want to exist in the same universe as you. Yet this impossible to detect substance holds galaxies together. It structures the entire cosmos. Without it, nothing would exist. Which raises an obvious question. If dark matter is this elusive, how do we catch it? Here's the paradox that keeps physicists awake at night. Dark matter only interacts through gravity. Gravity is the weakest force in nature, by far. Yet somehow, this weakest force is strong enough to build the entire universe. Think about how weak gravity actually is. A tiny fridge magnet can lift a paperclip against the gravitational pull of the entire Earth. One small magnet defeats the combined gravity of a planet weighing 6 septillion tons. That's how pathetically weak gravity is, compared to electromagnetic force. Now consider dark matter. It has no electromagnetic force, no strong nuclear force, no weak nuclear force, just gravity, the weakest force, Yet dark matter holds together objects containing trillions of stars. How? The answer lies in scale. Dark matter makes up for weakness with overwhelming quantity. There's so much dark matter in a galaxy that its combined gravitational pull becomes enormous. Think of it like this. One ant can't move a boulder. A trillion ants working together can move a mountain. Every galaxy sits inside a massive halo of dark matter. These halos extend far beyond the visible edges of galaxies. Our Milky Way's dark matter halo reaches out roughly 600,000 light-years. That's 3 times wider than the visible galaxy itself. Scientists have confirmed this through gravitational measurements. This halo contains approximately 1 trillion times the mass of our star. Written out, that's 1 trillion solar masses of invisible matter surrounding us, all of it pulling on the visible stars and gas through gravity alone. The combined force is powerful enough to prevent the galaxy from flying apart despite its rotation speed. But here's what's truly strange. Dark matter doesn't clump together like normal matter. Normal matter collides, heats up, and condenses into dense objects like stars and planets. Dark matter can't do this. It doesn't collide, it doesn't heat up, it doesn't condense efficiently. Instead, dark matter forms these enormous, diffuse halos. Scientists think dark matter particles are constantly zooming through these halos at hundreds of miles per second. They orbit, they pass through each other. They create a kind of invisible atmosphere around galaxies. Some researchers propose that dark matter might occasionally interact through forces we haven't discovered yet. Maybe there's a dark force that only affects dark matter. Maybe dark matter has its own version of electromagnetism. These ideas remain theoretical. Nobody has found evidence for dark forces. What we do know for certain is that gravity alone is sufficient to explain how dark matter structures the universe. Weak as gravity is, when you have 5 times more dark matter than normal matter, that weakness becomes overwhelming strength. The challenge now is proving dark matter exists beyond just gravitational evidence. That means detecting individual particles. That means building a trap so sensitive it can catch something that almost never touches anything. Scientists decided to build exactly that. Imagine trying to hear a whisper during a thunderstorm. Now imagine that whisper is 1,000,000 times quieter. That's the challenge physicists face trying to detect dark matter. They need silence, perfect silence, and they need to listen very carefully. The most ambitious dark matter detector is called LUX-ZEPLIN. Scientists built it 1 mile underground in an abandoned gold mine in South Dakota. Why underground? Because cosmic rays from space constantly bombard Earth's surface. These rays would create too much noise, too many false signals. Going underground blocks most cosmic radiation. The detector contains 7 tons of liquid xenon. Why xenon? Because it's extremely dense and pure. If a dark matter particle hits a xenon atom, it might create a tiny flash of light. That flash would be the first direct evidence that dark matter physically exists. But here's the problem. That flash would be incredibly faint. Scientists compare it to seeing a single candle burning on the moon observed from Earth. That's the level of sensitivity required. Any stray radiation would overwhelm the signal. So they surrounded the xenon tank with 72,000 gallons of ultra-pure water. This water blocks outside radiation. They cooled the xenon to -100 degrees. They eliminated every possible source of contamination. They used materials with almost 0 natural radioactivity. The detector can identify individual particle collisions. When something hits a xenon atom, it produces both light and electric charge. Scientists measure both signals. This helps distinguish dark matter from background radiation. The detector records millions of events every day. Computers analyze each one. They filter out cosmic rays. They eliminate natural radioactivity. They remove seismic vibrations from distant earthquakes. What remains should be dark matter collisions. Should be. Scientists have run this experiment for years. They've analyzed billions of events. They've pushed the sensitivity limits further than anyone thought possible. Result? 0 dark matter particles detected. Not one. The detector has been running for years in perfect silence, waiting for a signal that never comes. It's like setting up the most sophisticated microphone in history and hearing nothing but emptiness. Other experiments tried different approaches. Some used different materials. Some looked for different types of interactions. Some operated at different temperatures. All of them reported the same result: nothing. This creates a massive problem. Either dark matter particles are even more ghostly than we thought, or we're looking for the wrong thing entirely. Maybe dark matter doesn't interact with normal matter at all. Maybe the particle collisions we're waiting for simply don't happen. Scientists refuse to give up. They keep building bigger detectors, more sensitive equipment. They explore new theoretical possibilities. But with each failed experiment, the mystery deepens. If we can't detect dark matter directly, how can we prove it exists? That's when astronomers discovered something extraordinary, something that would provide the most dramatic evidence for dark matter anyone had ever seen. Let's talk about exactly how impossibly difficult dark matter detection actually is. Scientists need to detect a signal so weak it defies comprehension. They're trying to catch something that barely exists in our reality. When a dark matter particle hits a xenon atom, it transfers a tiny amount of energy. How tiny? About 1/10,000th the energy of a single photon of visible light. That's the collision scientists are trying to measure, an impact that weak shouldn't be detectable at all. To put this in perspective, the flash of light produced would be equivalent to detecting a single photon from a candle placed on the lunar surface. You'd be standing on Earth, looking up at the moon 239,000 miles away, trying to see one candle flame with your naked eye through the atmosphere during daytime. Impossible, right? That's what physicists are attempting with dark matter detectors. They're trying to see signals that shouldn't be visible to any instrument. The detectors use photomultiplier tubes. These devices can detect individual photons. When a single photon hits the tube, it creates a cascade of electrons. This amplifies the signal by millions of times. Even with this amplification, the dark matter signal barely rises above background noise. Background noise comes from everywhere. Radioactive atoms in the rock surrounding the detector decay randomly. Cosmic rays that penetrated the Earth's crust create secondary particles. The detector materials themselves contain trace amounts of radioactive elements. Even the scientists entering the room bring contamination. Every precaution has been taken. The water surrounding the xenon is purified to remove radioactive impurities. The detector walls are made from ultra-low background materials. Scientists shower and change clothes before entering the facility. They minimize time spent near the detector to reduce contamination. The xenon itself must be incredibly pure. Even one radioactive atom per trillion would create too much noise. Scientists spent years developing purification techniques to reach this level. They remove radon, krypton, and other contaminants atom by atom. Despite all these precautions, thousands of background events occur every day. Each one must be carefully analyzed. Is it a cosmic ray, natural radioactivity, equipment noise, or the one event in a billion that might actually be dark matter? Scientists developed sophisticated algorithms to identify dark matter signals. They look for specific patterns in how the energy is deposited. They check whether both light and charge signals appear simultaneously. They verify that the event came from inside the detector, not from external radiation. After years of operation, processing billions of collisions, filtering out every known source of background, the result remains the same: 0 confirmed dark matter detections. The candle on the moon remains invisible. The ghost particles continue to haunt us without leaving evidence. This failure isn't for lack of trying. This isn't poor equipment or bad techniques. This is reality telling us something profound. Dark matter is even stranger than our wildest theories predicted. Or perhaps we're chasing something that doesn't exist at all. But astronomers had one more trick up their sleeve. If they couldn't catch dark matter in a laboratory, maybe they could watch it in action across the cosmos. 20 years of searching, dozens of experiments, billions of dollars invested. Thousands of scientists dedicated their entire careers to finding dark matter particles. The results? Complete silence. LUX-ZEPLIN in South Dakota, XE-non in Italy, Panda X in China, DEAP in Canada, CDMS in Minnesota. Every major dark matter experiment around the world reports the same outcome. Nothing detected. No particles captured. No signals confirmed. This isn't just frustrating, it's scientifically terrifying. We built our entire model of the universe around dark matter. We calculated that it must exist. Our theories demand it. Yet, when we actually try to find it, the universe gives us nothing but emptiness. Some experiments claimed possible signals, brief moments of excitement. In 2011, an experiment called CoGNT detected unusual events. Could be dark matter. Within months, other experiments contradicted the results. False alarm. In 2013, CDMS saw 3 candidate events, 3 collisions that might have been dark matter. Statistical analysis showed they were probably background noise. Another false alarm. Every time scientists think they've found something, more careful analysis reveals mundane explanations. Cosmic rays, equipment malfunction, statistical fluctuation. The ghost remains uncaught. Scientists keep pushing the boundaries. They build larger detectors with more target material, more xenon, more germanium, more argon. The logic is simple. If dark matter rarely interacts, you need more material to increase your chances. LUX-ZEPLIN contains 7 tons. The next generation will contain 50 tons or more. They've also tried different detection methods. Some experiments look for annual modulation. The idea is that as Earth orbits around our star, we should move through dark matter streams at different speeds depending on the season. In summer, Earth's orbital motion adds to our motion through the galaxy. In winter, it subtracts. This should create a yearly fluctuation in detection rates. Result? No clear annual modulation detected. Some experiments claim to see hints, others see nothing. The evidence remains frustratingly ambiguous. Other experiments hunt for different types of dark matter particles. Maybe we're looking for the wrong kind. Scientists propose dozens of candidates: WIMPs, axions, sterile neutrinos, primordial black holes. Each requires different detection techniques. Each has been searched for. None have been found. The most disturbing possibility is that dark matter doesn't interact with normal matter at all, except through gravity. If that's true, we could search for 1 trillion years with increasingly sensitive detectors and never find a single particle. We might be building the most sophisticated instruments in human history to search for something that refuses to reveal itself. This failure has pushed some physicists toward radical alternatives. Maybe dark matter doesn't exist. Maybe our understanding of gravity is wrong. Maybe the universe is stranger than we can imagine. But before we abandon dark matter entirely, astronomers discovered something that provided the most spectacular confirmation anyone could ask for. They found dark matter separating from normal matter in real time. They watched it happen across millions of light years of space. The evidence was undeniable. 2006, astronomers detect something extraordinary. 2 massive galaxy clusters are colliding in deep space. This isn't a gentle merger. This is a violent head-on collision happening at 2,900 miles per second. That's over 10 million miles per hour. Each cluster contains thousands of galaxies, trillions of stars, vast clouds of superheated gas, and, if dark matter exists, enormous halos of invisible matter surrounding everything. This collision will become the most important observation in dark matter research. Scientists call it the bullet cluster. It's located 3.8 billion light-years away. The collision happened so long ago that Earth didn't exist yet when it began. We're seeing ancient history play out across the cosmos. Here's what makes this collision so revealing. When 2 galaxy clusters collide, different materials behave differently. The individual galaxies pass through each other relatively easily. Galaxies are mostly empty space. Stars within galaxies rarely collide because the distances between stars are enormous. But the hot gas between galaxies can't pass through easily. This gas makes up most of the normal matter in galaxy clusters. It's thin by Earth standards, but dense enough to interact. When the gas clouds collide, they slam into each other. They create shock waves. They heat up to hundreds of millions of degrees. The collision slows them down and leaves them behind in the center of the wreck. Astronomers can see this gas. It glows in X-rays. Observations show the gas concentrated between the two clusters, exactly where the collision happened. The gas marks the point of impact. Now, here's where it gets interesting. Astronomers can measure where the mass is located using gravitational lensing. Massive objects bend space-time. This bending deflects light from distant galaxies behind them. By measuring these distortions, scientists can map where mass exists, whether visible or invisible. They measured the bullet cluster's gravitational field. They found something shocking. The majority of the mass isn't where the gas is. The mass is surrounding the galaxies themselves. The mass passed right through the collision, almost unaffected. Think about what this means. The visible matter, the glowing gas, stayed behind in the collision. It interacted with itself and got stuck, but most of the gravitational mass kept moving. It passed through the collision, like the gas didn't exist. This is exactly what dark matter should do. Dark matter doesn't interact with normal matter. It doesn't collide with gas. It just floats through everything guided only by gravity. During the collision, the dark matter halos from both clusters passed through each other and continued onward with the galaxies. Scientists can literally see the separation. The gas sits in the middle. The gravitational mass sits on either side. They photographed the moment when dark matter and normal matter separated. This is direct visual evidence that invisible matter exists independently from visible matter. This observation is considered the strongest proof of dark matter's existence. It's hard to explain with modified gravity theories. The mass and the matter are in different places. You're not just seeing gravitational anomalies. You're watching matter behave as if there are two types, one that interacts and one that doesn't. Some scientists call this the smoking gun of dark matter research. But even with this evidence, the mystery deepens. We can see what dark matter does. We still can't detect what it's made of. The bullet cluster observation did something remarkable. It turned dark matter from an abstract mathematical necessity into something you can actually photograph. Scientists can point to a specific location in space and say, "There, that's where dark matter is." The technique uses gravitational lensing. Einstein predicted that massive objects bend spacetime itself. Light traveling through curved space follows curved paths. This means massive objects act like giant lenses, distorting the images of galaxies behind them. Astronomers photographed distant galaxies located far beyond the bullet cluster. They measured how the bullet cluster's gravity distorted these background galaxies. Some appeared stretched, some appeared as multiple images, some appeared brighter than they should. Each distortion reveals where mass is concentrated. The calculations are complex but confirmed. Scientists can reconstruct a gravitational map showing exactly where mass exists. They color-coded this map blue and overlaid it on images of the cluster. Blue represents where gravitational lensing is strongest. Blue shows where the mass is. Then they photographed the hot gas using X-ray telescopes. The gas glows pink in their images. They overlaid this pink gas map on the same image. Now you can see both visible matter and gravitational mass in one picture. The result is stunning. Pink sits in the middle where the collision occurred. Blue sits on either side where the galaxies are. The mass and the matter don't match. They're separated by millions of light years. You're literally looking at invisible matter that has moved away from visible matter. This separation proves several things. First, Dark matter exists as something distinct from normal matter. It's not just a mathematical trick. It's not just faulty gravity equations. There's actually something there. Second, dark matter barely interacts with itself. If dark matter particles collided strongly with each other, they would have been slowed down during the collision, just like the gas. But they weren't. They passed through almost unaffected. This means dark matter interactions, even with itself, must be extremely weak. Third, dark matter responds only to gravity. It followed the galaxies because galaxies create gravitational wells, but it ignored the gas completely, even though there's much more visible gas than visible stars. If dark matter interacted electromagnetically, it would have been affected by the charged particles in the gas. It wasn't. Scientists have found other colliding clusters showing similar separations. The Abell 2520 cluster, the Musketball cluster, Max J0025. Each one shows the same pattern: gas in the middle, gravitational mass surrounding the galaxies. Every collision confirms the same story. But here's what keeps scientists puzzled. We can see where dark matter is. We can measure how much there is. We can watch it move through space. But we still can't figure out what it's made of. Every attempt to capture individual particles fails. It's like being able to see a person's shadow, but never being able to see the person themselves. The shadow moves. It has shape. It proves someone is there, but the actual person remains invisible, no matter how hard you look. The bullet cluster proved dark matter exists. Now scientists need to figure out what it actually is. If dark matter exists, it must be made of particles. But what kind? Scientists have proposed candidates ranging from the absurdly heavy to the impossibly light. Let's explore the heavier end of the spectrum first. The most popular theory involves WIMPs. That stands for weakly interacting massive particles. Despite the silly name, WIMPs are serious candidates. These hypothetical particles would be 50 to 1,000 times heavier than a proton. That makes them heavier than any normal atom. Imagine a particle with the mass of an entire atom compressed into a space smaller than a proton. That's a WIMP. These particles would be incredibly dense. They'd be moving through space at hundreds of miles per second. When one passes through Earth, it would penetrate the entire planet without slowing down. WIMPs might occasionally hit normal atoms. Very occasionally. Scientists calculate that a WIMP traveling through your body has about a 1 in a trillion chance of hitting one of your atoms. Those odds are so low that you could live 1 billion lifetimes and never experience a single collision. Yet billions of WIMPs pass through you every second. With enough particles and enough time, rare events become inevitable. That's why scientists build massive detectors. They're not trying to catch one specific WIMP. They're creating opportunities for any WIMP to finally hit something. WIMPs would have been created in the Big Bang. In the first moments of the universe, temperatures were so extreme that exotic particles could form. Most of these particles decayed quickly. But WIMPs, if they exist, would be stable. They'd survive for the entire age of the universe. Scientists love WIMPs because they emerge naturally from theories about particle physics. Several extensions to the Standard Model predict WIMP-like particles. If these theories are correct, WIMPs must exist. Finding them would confirm decades of theoretical work. But there's a problem. We haven't found them. Despite 20 years of searching with increasingly sensitive detectors, no confirmed WIMP collisions have been detected. Either WIMPs interact even more weakly than predicted, or they don't exist at all. Some physicists propose even heavier candidates, particles thousands of times heavier than protons. These would be created in different processes and would be even rarer. They might account for only a fraction of dark matter. Nobody has found these either. Another possibility involves primordial black holes. What if dark matter isn't particles at all? What if it's countless tiny black holes formed in the Big Bang? These wouldn't be stellar black holes created from collapsed stars. These would be microscopic black holes created from density fluctuations in the early universe. A primordial black hole could have the mass of an asteroid compressed into a space smaller than an atom. Billions of these tiny black holes could permeate the galaxy, providing the missing gravitational mass without emitting any light. Scientists searched for evidence of primordial black holes. They looked for gravitational lensing effects. They searched for their gravitational influence on star formation. Recent observations have ruled out most mass ranges. Primordial black holes can't account for all dark matter, though they might contribute a small percentage. The heavier candidates have mostly been eliminated or pushed to the margins of possibility. That leaves scientists looking at the opposite extreme. What if dark matter particles aren't heavy at all? What if they're almost impossibly light? Here's an idea that sounds like fiction, but is taken seriously by physicists. What if dark matter isn't just invisible particles? What if it forms its own complete universe alongside ours? Think about our universe. We have atoms. Atoms combine into molecules. Molecules form complex structures. We have chemistry. We have electromagnetic forces that let atoms stick together. This complexity led to planets, stars, and eventually life. Now imagine dark matter has similar complexity. What if dark matter particles can combine into dark atoms? What if dark atoms form dark molecules? What if there are dark chemical reactions we can't observe? This isn't random speculation. We know dark matter can clump together through gravity. We see dark matter halos around galaxies. If dark matter has even weak self-interactions, it could form structures. Physicists call this the hidden sector theory. In this scenario, dark matter experiences forces we don't know about. Dark electromagnetism, dark strong force, dark weak force. These forces only affect dark matter particles. They're completely invisible to our instruments because our instruments are made of normal matter. Under hidden sector theories, dark matter could form dark planets, dark stars, maybe even dark galaxies within our galaxies. These structures would exist in the same physical space as Earth. They'd occupy the same cubic feet of volume, but they'd be completely undetectable except through gravity. You could be standing inside a dark matter mountain right now. Dark matter continents could exist overlapping with Earth's surface. You'd never know. You'd walk through them like they weren't there, because to normal matter, they aren't there. Some scientists take this further. Could dark matter support complexity? Could it form self-replicating structures? Could there be dark matter life? This sounds absurd, but consider the numbers. If dark matter is 85% of all matter, why would it be simpler than our 15%? Maybe we're the simple universe. Maybe the dark sector has far richer complexity than anything we've discovered. We'd never know because we can only detect its gravity. Here's the most disturbing part. Dark matter could have its own history completely separate from ours. While our universe was forming stars and galaxies, the dark universe was forming its own structures. These structures evolved according to their own physics. They created their own landscapes. Right now, Earth could be passing through dark matter structures as we orbit our star. Dark matter currents could flow past us. Dark matter storms could rage in our cosmic neighborhood. We detect nothing beyond slight gravitational effects. Some researchers propose that dark matter might occasionally interact with itself more strongly than it interacts with us. This would allow dark matter to cool down and form more concentrated structures. Small dark matter clumps could drift through our solar system. One might pass through Earth every few years. If a dark matter clump passed through your body, you wouldn't feel anything, but its gravity would be measurable by sensitive instruments. Scientists have searched for these transient gravitational signals. So far, nothing confirmed. The hidden sector theory makes testable predictions. If dark matter has its own forces, those forces might leak into our sector in specific ways. Certain particle collisions at CERN might produce dark sector particles. These would appear as missing energy, just like normal dark matter, but the patterns would be different. Physicists are searching for these signatures. They're looking for hints that dark matter has structure beyond simple particles. If they find evidence, it would mean reality is far stranger than we imagined. Two universes occupying the same space, forever separated except by gravity. But even without that complexity, dark matter has already shaped everything you see. Without it, you wouldn't exist to ask these questions. Let's push this idea to its absolute limit. Some physicists propose that dark matter exists in a parallel dimension, not a dimension in the science fiction sense. A real, physical dimension we can't access. We experience three spatial dimensions: length, width, height. We move freely through these dimensions. But what if additional dimensions exist curled up so small that we can't perceive them? String theory predicts this. Mathematics suggests up to 7 extra dimensions beyond our 3. Dark matter might exist partly or entirely in these extra dimensions. From our perspective, dark matter appears as particles in our 3 dimensions, but most of its existence extends into dimensions we can't see. It's like viewing a sphere passing through a flat plane. The flat beings would only see a circle that grows and shrinks. They'd never perceive the full sphere. This could explain why dark matter is so elusive. We're trying to study something that mostly exists outside our dimensional space. We only interact with the tiny fraction that overlaps with our dimensions. The bulk of dark matter's properties remain hidden in higher dimensions. Gravitational force might be the only interaction that works across dimensions. Electromagnetic force, strong force, weak force, these might be locked to our 3 dimensions. But gravity could propagate through all dimensions. That's why we only detect dark matter through gravity. This theory makes a stunning prediction. If dark matter exists in extra dimensions, then gravity itself might leak into those dimensions. This would make gravity appear weaker in our 3 dimensions than it should be. Scientists have tested this. They've measured gravitational force at microscopic scales to see if it deviates from predictions. So far, gravity behaves exactly as Einstein predicted, down to the smallest distances we can measure. Another test involves particle accelerators. If extra dimensions exist, high-energy collisions might produce particles that escape into those dimensions. These particles would carry away energy, appearing as a deficit in our measurements. Physicists at CERN have searched for this missing energy signature. Results remain inconclusive. The parallel dimension theory faces challenges. It's mathematically complex. It's difficult to test. It makes predictions that are hard to distinguish from simpler explanations, but it remains a possibility. Here's the philosophical implication. If dark matter exists in extra dimensions, then reality is far more expansive than we perceive. We'd be living in a shadow of a larger cosmos. Everything we see would be a projection of something bigger. You'd be like a character in a book, aware only of the page you're on, completely unaware of the reader holding the book in a higher dimension. Your entire existence plays out on a flat surface while a vast 3-dimensional world surrounds you invisibly. This isn't just poetry. This is serious physics trying to explain why 85% of the universe hides from us. Maybe it's not hiding. Maybe we're just looking in the wrong dimensions. But regardless of where dark matter exists or what it's made of, one fact remains undeniable. Without dark matter, the universe would be completely different. In fact, without dark matter, nothing would exist at all. 13.8 billion years ago, the universe began. In that first moment, everything that would ever exist was created. Energy, matter, space itself, time itself, and according to our best theories, dark matter. In those earliest moments, the universe was incredibly uniform. Measurements show that density variations were only 0.001%, almost perfectly smooth. Think of a completely flat ocean with waves only a few inches high. That's how uniform the early universe was. This creates a massive problem. If the universe was that smooth, how did it develop structure? How did galaxies form? How did stars ignite? How did planets coalesce? You can't build structures from uniformity. You need clumps. You need variations. You need some regions denser than others. Here's where dark matter becomes essential. Regular matter in the early universe was trapped. It was locked in a hot plasma of electrons and photons. These particles bounced off each other constantly. They couldn't clump together. Light pressure kept pushing them apart. Any density variation in normal matter got erased by radiation pressure. Dark matter faced no such problem. Dark matter doesn't interact with light. It doesn't feel radiation pressure. So, while normal matter remained stuck in a boiling plasma, dark matter was already beginning its work, confirmed by computer simulations of the early universe. Wherever dark matter happened to be slightly more concentrated, gravity pulled more dark matter toward it. These concentrations grew. They became denser. They started forming structures. All of this happened invisibly. No light marked these events. No telescope could have detected them. But the gravitational framework was being built. 380,000 years after the Big Bang, the universe finally cooled enough for normal matter to break free from the plasma. Electrons and protons combined into neutral atoms. Light could finally travel freely. This is the moment we see as the cosmic microwave background radiation. When normal matter became free, it found a universe already structured by dark matter. Invisible scaffolding filled space. Dark matter halos marked the locations where the first galaxies would form. Normal matter fell into these gravitational wells like water finding valleys. Think of it this way. Dark matter prepared the mold. Normal matter filled the mold. Without the mold, normal matter would have dispersed evenly through space. No structures, no clumps. Just a thin, uniform gas expanding forever into emptiness. The first stars formed inside dark matter halos. These stars created heavier elements through nuclear fusion. They exploded as supernovas, spreading these elements through space. Subsequent generations of stars formed from this enriched material. Eventually, planets formed. On at least one planet, life emerged. Every step of this process required dark matter's gravitational framework. Without dark matter halos concentrating normal matter, stars wouldn't have formed. Without stars, there would be no heavy elements. Without heavy elements, there would be no rocky planets. Without rocky planets, there would be no life as we know it. You are made of atoms forged in stars. Those stars only exist because dark matter created the conditions for their birth. The calcium in your bones, the iron in your blood, the oxygen you breathe, all came from stars that owed their existence to invisible matter. Our entire Milky Way galaxy sits inside a halo of dark matter extending 600,000 light-years across. This halo contains about 1 trillion solar masses of dark matter. Its gravity holds our galaxy together. Without it, the stars would fly apart. Our local group of galaxies would dissolve. The cosmic web of galaxy clusters would unravel. Dark matter makes up the invisible foundation of everything you see. Every galaxy, every star, every planet, every living thing. We live in a universe where the visible is just decoration. On an invisible framework, we're the small part riding on top of the big part. But the story isn't over. Scientists continue hunting for answers. Let's rewind to the very beginning. The first fraction of a second after the Big Bang, the universe was unimaginably hot, trillions of degrees, so hot that matter as we know it couldn't exist. Just pure energy bouncing around in a tiny space smaller than an atom. As the universe expanded, it cooled. Within the first second, quarks formed. These quarks combined into protons and neutrons. But something else was happening simultaneously. Dark matter particles were being created. Scientists believe dark matter formed in the first microsecond of existence, confirmed by mathematical models of the early universe. Here's the critical difference. Normal matter was immediately trapped. Photons, electrons, and protons formed a thick soup of interacting particles. This soup was called the photon-baryon plasma. Everything bounced off everything else. Light couldn't travel more than a tiny distance before hitting something. Imagine trying to walk through a crowd so dense you can't move. Every step, you bump into someone. That was normal matter in the early universe. Stuck, unable to separate, unable to clump together because radiation pressure kept shoving it apart. Dark matter experienced none of this. From the moment dark matter particles formed, they were already free. They didn't interact with the plasma. They didn't bounce off photons. They moved through the chaos like ghosts walking through walls. While normal matter remained trapped for 380,000 years, dark matter got a massive head start. This head start changed everything. Even tiny variations in dark matter density could begin growing immediately. Regions with slightly more dark matter attracted more dark matter through gravity. These regions became denser. The denser they became, the more strongly they attracted surrounding dark matter. Think of it like a snowball rolling down a hill. It starts tiny, but as it rolls, it gathers more snow. It gets bigger. The bigger it gets, the more snow it picks up. Dark matter structures grew through exactly this process. Gravitational accumulation without resistance. Computer simulations show this beautifully. Scientists can run the entire history of the universe on supercomputers. They input the conditions at the Big Bang. They let gravity and physics run forward for 13.8 billion simulated years. They watch what happens. Without dark matter, the simulations produce an empty universe. Normal matter disperses evenly. Nothing clumps, nothing forms. With dark matter included, the simulations produce a universe that looks remarkably like ours. Filaments of galaxies, clusters connected by bridges of matter, vast empty voids between structures, the cosmic web. By the time normal matter broke free from the plasma, dark matter had already created an intricate network of gravitational potential wells. These wells acted like cups waiting to be filled. When normal matter suddenly became free to move, it rushed toward these pre-existing structures. The first stars formed in the densest dark matter halos roughly 100 million years after the Big Bang. These first stars were massive, hundreds of times larger than our star. They burned hot and died young, but they created the conditions for everything that followed. Without dark matter's head start, those first stars would have formed much later, maybe billions of years later, maybe never. The timeline of cosmic evolution depends entirely on dark matter doing its work early. You exist because dark matter got a head start of 380,000 years. That might not sound like much in the context of a 13.8 billion-year-old universe, but it was enough. That head start built the framework for everything. But what does this invisible framework actually look like up close? Our Milky Way galaxy contains 200 billion stars. These stars form a disk about 100,000 light-years across. Beautiful spiral arms swirl through this disk. At the center sits a supermassive black hole 4 million times heavier than our star. This is what we see. But the visible galaxy is just the tip of the iceberg. The Milky Way actually extends much farther. It's wrapped in an enormous halo of dark matter that reaches out 600,000 light-years, 6 times wider than the visible galaxy. This halo contains approximately 1 trillion solar masses of invisible matter. To put that in perspective, the halo has about 10 times more mass than all visible stars combined. We're not living in a galaxy with some dark matter around it. We're living inside a dark matter structure that happens to have some visible matter sprinkled in the center. Right now, you're inside this dark matter ocean. Earth orbits around our star at about 47,000 miles per hour. Our star orbits the galactic center at about 500,000 miles per hour. The entire Milky Way is moving through intergalactic space at over 1 million miles per hour. Through all of this motion, we're swimming through dark matter. The dark matter isn't uniformly distributed. It's densest at the galactic center and gets thinner as you move outward. Near our star's location, roughly 26,000 light-years from the center, the dark matter density is about 1 proton mass per cubic inch. That sounds incredibly thin. It is, but it's enough. Scientists calculate that approximately 100 billion dark matter particles pass through Earth every second. Through every square inch of Earth's surface. That's billions passing through your body right now. You'll never feel a single one. The dark matter halo isn't static, it's dynamic. Dark matter particles orbit through the galaxy, just like stars do, but their orbits are more chaotic. Some move in highly elliptical paths. Some plunge toward the galactic center and back out. Some orbit in the opposite direction from the galaxy's rotation. Think of it like cars on a highway versus birds in the sky. Stars move in organized lanes around the galactic center. Dark matter particles move in all directions at various speeds. The overall structure remains stable, but individual particles follow complex trajectories. Recent research suggests the dark matter halo might contain substructure, smaller clumps of dark matter embedded within the larger halo. These subhalos could be remnants of smaller galaxies that merged with the Milky Way billions of years ago. Their stars got absorbed into our galaxy. Their dark matter halos remained partially intact. If these subhalos exist, one might pass through our solar system occasionally. The gravitational effects would be subtle, but potentially detectable. Scientists search for sudden, tiny changes in planetary orbits or asteroid paths that might indicate a dark matter clump passing nearby. Some theories propose that dark matter forms thin, dense streams flowing through the galaxy. These streams would be the debris trails from disrupted satellite galaxies. If Earth passes through one of these streams, the local dark matter density could temporarily spike. This might improve detection chances in underground laboratories. The entire local group of galaxies, which includes the Milky Way, Andromeda, and about 50 smaller galaxies, sits inside an even larger dark matter structure. This structure contains roughly 2 trillion solar masses and extends several million light-years across. Everything we consider our cosmic neighborhood exists within this invisible architecture. Andromeda, our nearest large galactic neighbor, has its own dark matter halo. In about 4 billion years, the Milky Way and Andromeda will collide. Their dark matter halos will merge first. The collision will take hundreds of millions of years. The visible galaxies will eventually combine into one enormous elliptical galaxy, but the dark matter halos will have already united. Every galaxy we observe through telescopes lives inside its own dark matter ocean. Galaxy clusters sit inside even larger dark matter structures. The entire universe is organized around invisible scaffolding we can barely detect. We're fish swimming in an ocean we can't see. But scientists refuse to stop looking. They're trying new approaches, new particles, new theories, new technologies to finally catch a glimpse of the water we're swimming in. WIMPs have dominated dark matter research for decades, but after years of null results, physicists are exploring alternative candidates. 2 particularly interesting possibilities are axions and sterile neutrinos. Both would be radically different from WIMPs. Let's start with axions. These hypothetical particles would be incredibly light, about 1 trillion times lighter than an electron. That's almost massless. An individual axion would barely exist at all. But here's the trick. There would be an enormous number of them. Scientists calculate that approximately 10 billion axions would occupy every cubic inch of space in our galaxy. That's an absurd density. You'd have more axions in your bedroom than there are stars in the Milky Way. Despite being nearly massless individually, their collective mass would be enormous. Axions would behave more like waves than particles. At such low masses, quantum mechanics dominates. Individual axions would spread out over large regions of space. They'd overlap with each other. They'd form a kind of quantum field permeating the galaxy. Here's where it gets strange. This field would oscillate. It would vibrate at a specific frequency determined by the axion's mass. The entire dark matter halo would be humming with this oscillation. We don't feel it because the frequency is extremely low, but sensitive instruments might detect it. Scientists built an experiment called ADMX, the Axion Dark Matter experiment. It uses a device called a resonant cavity. This is essentially a highly tuned radio receiver. If axions exist, their oscillations might convert to electromagnetic waves inside a strong magnetic field. ADMX is trying to detect those waves. The challenge is finding the right frequency. Nobody knows the exact mass of the axion. Different masses produce different frequencies. ADMX must scan through billions of possible frequencies. Each frequency takes time to test. The experiment has been running for years and has covered only a fraction of the possible range. So far, no axions detected, but the search continues. If axions exist, they could solve multiple mysteries simultaneously. They explain dark matter. They also solve a problem in particle physics called the strong CP problem. Finding axions would be a double breakthrough. Now let's talk about sterile neutrinos. Regular neutrinos are known particles. They're produced in nuclear reactions. Trillions of neutrinos pass through you every second from our star. They barely interact with matter, which makes them similar to dark matter already. But regular neutrinos are too light and too fast to be dark matter. They don't clump gravitationally. Scientists propose that heavier versions might exist. These are called sterile neutrinos. They'd be thousands of times heavier than regular neutrinos, but still much lighter than protons. Sterile neutrinos would be even more ghostly than regular neutrinos. They'd only interact through gravity. No weak force, no electromagnetic force, nothing but gravity. This makes them perfect dark matter candidates. It also makes them nearly impossible to detect directly. However, sterile neutrinos might very rarely decay. When they decay, they'd produce regular particles we can detect. One decay product would be an X-ray photon with a very specific energy. Scientists have searched for this signal in X-ray observations of galaxy clusters. In 2014, multiple research teams reported detecting an unusual X-ray line from several galaxy clusters. The energy matched predictions for sterile neutrino decay. Excitement spread through the physics community. Finally, direct evidence of dark matter particles. But the signal was weak. Other teams couldn't confirm it. The observation required pushing instruments to their limits. Systematic errors could explain the signal. The debate continues. Some scientists believe it's real. Others remain skeptical. Both axions and sterile neutrinos represent a shift in thinking. Maybe dark matter isn't made of heavy particles. Maybe it's made of particles so light they act completely differently from normal matter. Maybe that's why we haven't found it. We've been looking for the wrong thing in the wrong way. Scientists are expanding the search. New experiments target ultralight dark matter. New telescopes look for decay signals. New theories propose exotic combinations of different dark matter types. Maybe dark matter isn't just one particle. Maybe it's multiple particles working together. But there's another approach. Instead of catching dark matter particles, what if we create them? Deep beneath the border between France and Switzerland, a machine called the Large Hadron Collider smashes protons together at nearly the speed of light. These collisions recreate conditions from the first moments after the Big Bang. If dark matter particles were created back then, they might be created here too. The LHC is a circular tunnel 17 miles in circumference. Protons race around this tunnel 40,000 times per second. Powerful magnets guide them. When scientists want to create collisions, they steer two beams of protons into each other head-on. The collision energy is enormous, about 13 trillion electron volts. That's enough energy to create new particles from pure energy according to Einstein's equation. Regular collisions produce hundreds of known particles, quarks, electrons, photons, everything we expect. But scientists aren't looking for known particles. They're searching for missing energy. Here's the logic. If dark matter particles are created in a collision, they'd immediately escape the detector. They wouldn't interact with the detection equipment. they'd leave no trace. However, energy must be conserved. Scientists measure all the energy going into a collision. They measure all the visible energy coming out. If these don't match, something invisible carried energy away. That something might be dark matter. Every collision at the LHC is recorded by massive detectors. Atlas, CMS. These detectors are 3 stories tall and weigh thousands of tons. They measure particles with incredible precision. They track every photon, every electron, every quark produced in the collision. After billions of collisions, scientists analyze the data. They look for events where energy appears to vanish, events where the visible products don't add up to the initial energy. These are called missing energy events. They're rare, but they happen. The problem is distinguishing dark matter from other particles that also escape detection. Regular neutrinos also carry away energy invisibly. They're produced in many collisions. Scientists must carefully subtract known neutrino production to find any excess. After years of data collection, the LHC has found no conclusive evidence of dark matter production. Some hints appeared, some anomalies in the data, but nothing definitive. Every promising signal eventually found mundane explanations. This null result tells us something important. If dark matter particles exist, they're either too heavy to be created at LHC energies, or they're produced through processes we don't understand. The LHC operates at the highest energies humans have ever achieved. If dark matter is heavier than what we can create here, we might never directly produce it. Some physicists propose that dark matter particles are much lighter than LHC energies. In that case, they'd be produced abundantly, but they'd be impossible to distinguish from background noise. Too many particles would be created. The signal would drown in data. Others suggested that dark matter production requires special conditions beyond simple high-energy collisions. Maybe dark matter only forms in the presence of certain fields. Maybe it requires specific quantum states. The LHC wasn't designed with these conditions in mind. There's another possibility. Maybe dark matter isn't made of particles created through collisions at all. Maybe it's something fundamentally different. Something that can't be produced in particle accelerators. No matter how powerful, the LHC will continue running through the 2030s. Scientists will upgrade the detectors. They'll increase collision energies. They'll analyze more data. But the longer we search without finding anything, the stranger the truth becomes. What if our entire approach is wrong? What if we're searching for something that doesn't exist? That brings us to a radical alternative theory. Here's a philosophical problem that keeps physicists awake at night. How do you prove something invisible exists when you can't catch it? Every experiment designed to find dark matter particles has failed. Every detector comes up empty. Every accelerator finds nothing unusual. Scientists are left searching for the signature of nothing. They're looking for what's missing rather than what's present. This is fundamentally different from normal physics. Usually, you discover something by detecting it. You see a signal, you measure an effect, you find evidence. With dark matter, the evidence is absence, missing energy, missing mass, gravitational effects without visible sources. It's like being a detective investigating a crime where the only clue is what didn't happen. This creates a verification problem. How do you distinguish between something invisible and something that doesn't exist? If I claim there's an invisible dragon in my garage, but it has no mass, makes no sound, and leaves no traces, how is that different from no dragon at all? Dark matter avoids this trap because it does have measurable effects. Gravity, galaxy rotation curves, gravitational lensing, the bullet cluster. These are real observations that demand explanation. But they're indirect. We're inferring dark matter's existence from its gravitational fingerprints. Scientists develop sophisticated techniques for finding these fingerprints. They map how galaxies move within clusters. They measure tiny distortions in light from distant quasars. They analyze fluctuations in the cosmic microwave background radiation. Every technique points to the same conclusion. Something invisible is there. But here's the unsettling part. All these observations only prove that something gravitational exists. They don't prove its particles. They don't prove its matter in any conventional sense. They just prove gravity is doing things that visible matter alone can't explain. What if the signature we're detecting isn't actually matter? What if it's something else entirely? This question leads to one of the most controversial alternatives to dark matter: modified gravity. Instead of inventing invisible particles, some physicists propose changing how gravity works. The idea is simple. At very large distances or very low accelerations, gravity might behave differently than Newton or Einstein predicted. In this scenario, there's no dark matter at all. The galaxy rotation curves that convinced us dark matter exists are actually showing us that our gravity equations are incomplete. The gravitational lensing we observe isn't from invisible mass. It's from space-time, curved by modified gravitational rules. This would be revolutionary. It would mean Einstein's general relativity, one of the most successful theories in physics, needs correction. It would overturn a century of confirmed predictions. But it would solve the dark matter problem without adding mysterious invisible particles. The signature of nothing would then be reinterpreted. We're not detecting invisible matter. We're detecting the failure of our gravitational theories at certain scales. The missing mass is really missing physics. But there's a massive obstacle standing in the way of this idea. It has to explain everything dark matter explains: galaxy rotation, gravitational lensing, the bullet cluster, cosmic structure formation. That's an enormous challenge. Can modified gravity pass all these tests? Or does the evidence really demand invisible matter? This debate has raged for decades. The answer determines the future direction of fundamental physics. 1983. Israeli physicist Mordechai Milgrom proposes a radical idea. What if Newton's laws stop working at very low accelerations? Not slightly wrong, fundamentally different. He called his theory MOND, Modified Newtonian Dynamics. The concept is elegant. In normal situations, like our solar system, gravity works exactly as Newton described. But when accelerations become extremely tiny, like at the edges of galaxies, gravity gets stronger than predicted. Stars feel a stronger pull than Newton would calculate. This extra pull explains their unexpectedly high speeds. No dark matter needed, just modified physics. Think about how appealing this is. Instead of inventing an entirely new type of matter that nobody can detect, you make a small adjustment to existing laws. Occam's razor would favor this approach. The simplest explanation is usually correct. Milgrom showed that MOND perfectly matches galaxy rotation curves. The fit is remarkable. You input a galaxy's visible mass, and MOND predicts exactly how fast stars should orbit at any distance. The predictions match observations beautifully. No invisible matter required. MOND has one parameter, one number that sets where the modification kicks in. That number is an acceleration of about 100 billionth of Earth's surface gravity. Below this threshold, gravity strengthens. Above it, gravity follows Newton's laws exactly. This single parameter works for all galaxies. Scientists tested MOND against hundreds of galaxies, different sizes, different shapes, different distances. MOND explained them all using visible matter alone. This is impressive. Dark matter models need to fine-tune invisible halos for each galaxy. MOND uses one universal rule, but MOND has serious problems. First, it's not a complete theory. MOND describes how objects move. It doesn't explain why gravity should change at low accelerations. There's no underlying physical mechanism, no fundamental principle. It's an empirical rule without theoretical foundation. Einstein's relativity is more than equations. It's based on fundamental principles about space-time. MOND lacks this depth. It's a patch on Newton's laws without explaining what broke them. Second, MOND struggles with galaxy clusters. These massive structures contain thousands of galaxies. Their velocities suggest far more mass than visible matter. MOND can explain some of this, but not all. you still need about twice as much mass as you can see. That means even with MOND, you need some invisible matter, just less than standard dark matter models require. Third, MOND has no clear relativistic version. Newton's laws are approximations. Einstein's general relativity is the complete theory of gravity. Scientists tried to create relativistic versions of MOND. These attempts produced multiple competing theories. None fully work. None make predictions as clean as MOND does in the Newtonian limit. Fourth, and most devastating, MOND cannot explain the bullet cluster. Remember that collision? The gravitational mass separated from the visible matter. With MOND, gravity is produced by visible matter. The gravitational center should be where the visible matter is, but it's not. The observations clearly show mass where there's no visible matter. MOND supporters proposed explanations. Maybe there's some undiscovered neutrino mass accounting for the missing matter in the bullet cluster. Maybe the observations have systematic errors. But these explanations feel forced. They're adding complications to save a theory that promised simplicity. Despite these problems, MOND won't die. It keeps matching galaxy rotation curves too precisely. That can't be coincidence. Dark matter models struggle to reproduce MOND's predictive power. They need to carefully tune dark matter distributions for each galaxy. MOND uses one formula for everything. This suggests something interesting. Maybe MOND is telling us something true about gravity, even if it's not the complete answer. Maybe dark matter exists, and gravity is modified. Maybe we need both to explain all observations. But that would be the worst-case scenario, adding complexity on top of complexity. If that's true, we understand even less than we thought. Scientists tried everything to make modified gravity work. They built elaborate mathematical frameworks. They proposed multiple versions of MOND with relativistic corrections. They invented new fields and forces to explain why gravity would change at low accelerations. None of these attempts fully succeeded. The most sophisticated version is called TeVeS, Tensor Vector Scalar Gravity. It's mathematically complex. It adds new fields to Einstein's equations. These fields only become important at very low accelerations. When accelerations are high, TeVeS reduces to standard general relativity. When accelerations are tiny, it reproduces MOND's predictions. TeVeS seemed promising. It made testable predictions. Scientists compared these predictions to observations of gravitational lensing. Light from distant galaxies bends around massive objects in the foreground. The amount of bending reveals how much mass is present. In standard cosmology, with dark matter, the lensing observations make sense. Massive dark matter halos bend light exactly as much as we observe. TeVeS made different predictions. The lensing should be somewhat weaker because there's less total mass once you remove dark matter. Observations contradicted TeVeS predictions. The lensing was stronger than TeVeS allowed. Either the theory needed adjustment, or there really is invisible mass creating the extra lensing. Scientists tried adjusting TeVeS. Each adjustment made the theory more complicated and less elegant. Then came the ultimate test, gravitational waves. In 2017, astronomers detected gravitational waves from two neutron stars colliding. These waves ripple through space-time itself. Einstein predicted them a century ago. Their detection confirmed general relativity in a new regime. But here's what killed many modified gravity theories. The gravitational waves arrived at Earth at almost the same time as light from the same collision. The time difference was less than 2 seconds after traveling 130 million light-years. This means gravitational waves travel at the speed of light. Confirmed, many modified gravity theories predicted gravitational waves should travel at different speeds than light. TeVeS was one of them. The observation ruled out these theories immediately. If gravity is modified, the modification must still preserve gravitational wave speed. That's an enormous constraint. Modified gravity advocates went back to the drawing board. They developed new theories compatible with gravitational wave observations, but each new constraint makes the theories more complex. They're losing their original appeal, simplicity. The bullet cluster remains the strongest evidence against modified gravity. Multiple colliding galaxy clusters show the same pattern. Gravitational mass separated from visible matter. Modified gravity cannot easily explain this. The mass should follow the matter, because in these theories, matter creates the modified gravitational field. Some physicists proposed that modified gravity might work differently in dynamical situations like collisions. Maybe the modification needs time to adjust. Maybe there are additional effects during violent events. These explanations sound increasingly desperate. Others suggested combining modified gravity with some invisible matter, not as much as standard dark matter models require. Maybe 10 or 20% instead of 85%. This hybrid approach reduces dark matter's role while keeping Mond's successful predictions for galaxy rotation. But now you have the worst of both worlds. Modified gravity plus invisible matter. Two mysteries instead of one. Why would nature work this way? It's not impossible, but it's unsatisfying. The scientific community has largely moved away from pure modified gravity. Most physicists now believe dark matter exists, but Mond's successes still puzzle everyone. How does it predict galaxy rotation so accurately if dark matter is the real answer? This remains unexplained. Some researchers propose that dark matter interacts with itself in ways that naturally produce Mond-like distributions in galaxies. This would be dark matter that behaves unusually, not the simple, non-interacting particles we've been searching for, something more complex. Every attempt to solve the dark matter mystery seems to lead to more questions. What if the truth is even stranger than dark matter or modified gravity? Here's the nightmare scenario that physicists rarely discuss publicly. What if we're wrong about both dark matter and gravity? What if the universe operates on principles we haven't discovered yet? What if our entire framework for understanding reality needs to be rebuilt? Consider what we actually know for certain. Galaxies rotate faster than visible matter can explain. Gravitational lensing shows more mass than we can see. Galaxy clusters hold together despite insufficient visible matter. The universe's structure formed too quickly given the amount of visible matter available. These are observations, facts, confirmed repeatedly. Everything else is interpretation. We interpret these observations through our understanding of gravity and matter. We assume Einstein's equations work everywhere. We assume matter behaves consistently at all scales. We assume the laws of physics we've discovered on Earth apply throughout the cosmos. What if one of these assumptions is wrong? Not slightly wrong, fundamentally mistaken. This has happened before in science. Newton's gravity worked perfectly for centuries. Then Einstein showed it was incomplete. Newtonian physics is still useful, but it's an approximation of deeper truth. Maybe Einstein's general relativity is also an approximation. Something more fundamental might operate at galactic scales. We wouldn't know because we can't test general relativity perfectly at those distances. Our solar system is too small. Galaxy clusters are too far away. We're extrapolating from limited data. Or maybe our understanding of matter is incomplete. We know about quarks, electrons, photons. We've found the Higgs boson. We think we understand the fundamental particles. But quantum field theory has gaps, problems without solutions. Maybe we're missing entire categories of particles or fields. Dark matter might be our generation's luminiferous ether. In the 1800s, scientists believed light traveled through an invisible substance called ether. Everyone accepted it. Experiments searched for it. Theories depended on it. Then Einstein showed ether doesn't exist. Space-time itself carries light waves. Imagine if future scientists look back at dark matter the same way. They invented invisible matter to explain observations they didn't understand. Maybe the real explanation is completely different. maybe we're not even asking the right questions. Here's what makes this terrifying. We're building cosmology on dark matter. We're constructing models of the universe's history that assume dark matter exists. If we're wrong, decades of work collapses. Thousands of papers become obsolete. Entire research programs pursue incorrect ideas. But this is also exciting. Science advances through revolutions, moments when everything we thought we knew gets overturned. Quantum mechanics revolutionized physics in the 1920s. Relativity revolutionized it in the 1910s. Maybe we're due for another revolution. The signs are there. We can't detect dark matter despite decades of trying. Modified gravity doesn't work either. Both approaches have failed. When two opposite solutions both fail, maybe the problem itself is wrong. Maybe we're missing something fundamental about how the universe works. Some physicists explore radical alternatives. What if space-time has more dimensions than we perceive? What if quantum mechanics and gravity merge in unexpected ways at galactic scales? What if consciousness plays a role in cosmological observations? These ideas sound crazy. So did quantum mechanics when it was first proposed. The point isn't that any specific alternative is correct. The point is that we might need to think completely differently. Step outside our assumptions. Question everything. That's uncomfortable. Scientists spent careers mastering current theories. Admitting those theories might be wrong feels like wasting a life's work. But that's how science progresses. Each generation thinks they've figured it out. Each generation discovers they missed something crucial. We're probably no different. Future physicists will look back and wonder how we missed the obvious answer. The question is, what will that answer be? Will it be dark matter finally detected? Will it be modified gravity that actually works? Or will it be something nobody has imagined yet? The next decade will be crucial. New telescopes are coming online. New experiments are starting. New data will force us toward an answer. Let's look at what's coming. July 2023. The European Space Agency launched a telescope named Euclid. This spacecraft will spend 6 years creating the most detailed map of dark matter ever attempted. It's going to change everything we think we know. Euclid orbits about 1 million miles from Earth at a location called L2. This is a gravitational balance point where spacecraft can maintain stable positions. The telescope has a mirror just over 4 feet wide. Not huge by telescope standards. But size isn't what makes Euclid special. Euclid is designed specifically to map the invisible universe. It will photograph 1/3 of the entire sky. That's billions of galaxies. For each galaxy, it will measure precise shapes and distances. From this data, scientists will reconstruct where dark matter is located throughout cosmic history. The technique uses weak gravitational lensing. Dark matter's gravity bends light from distant galaxies. These distortions are tiny. Individual galaxies show barely noticeable stretching or warping. But when you analyze millions of galaxies statistically, patterns emerge. Imagine looking at trees in a forest through heat waves rising from the ground. Each tree looks slightly distorted. The distortions seem random. But if you measure millions of trees, you can reconstruct exactly how the heat waves are flowing. That's what Euclid does with gravitational lensing. The telescope measures galaxy shapes with incredible precision. It detects distortions of less than 1%. It can identify weak lensing effects invisible to human eyes. Computer algorithms process these shapes, extracting dark matter information from subtle statistical patterns. Euclid will reveal the cosmic web in unprecedented detail. This web is the large-scale structure of the universe. Galaxies aren't randomly scattered through space. They form filaments, long strands of galaxies connected by dark matter bridges. Between these filaments lie enormous voids, empty regions, hundreds of millions of light years. Across, dark matter forms the skeleton of this web. Visible matter traces the dark matter distribution. By mapping visible galaxies, Euclid maps invisible structure. The data will show exactly how dark matter is distributed throughout billions of light years of space. But Euclid does more than map static structure. It measures cosmic history. Light from distant galaxies takes billions of years to reach us. When we observe distant galaxies, we see them as they were in the past. By comparing galaxies at different distances, Euclid traces how dark matter evolved over time. This is crucial for understanding what dark matter is. Different dark matter candidates predict different evolution patterns. If dark matter is made of WIMPs, the cosmic web should evolve in specific ways. If it's axions, the evolution would be different. Euclid's data will constrain these possibilities. The telescope also measures something called baryon acoustic oscillations. These are subtle patterns in how galaxies cluster. The patterns are fossil evidence from sound waves in the early universe. Dark matter influences these patterns. By measuring them precisely, scientists learn about dark matter's properties. Euclid's first images arrived in late 2023. They're stunning. Galaxies shine with incredible clarity. Background galaxies show obvious lensing effects. Even these preliminary images reveal new details about cosmic structure. Over the next 6 years, Euclid will accumulate enormous amounts of data. Thousands of scientists will analyze this information. They'll create three-dimensional maps showing dark matter distribution across cosmic history. They'll test dark matter models. They'll search for alternatives to dark matter. The spacecraft will observe how galaxy clusters form, how dark matter halos merge, how the cosmic web evolves. Every observation provides new constraints on dark matter theories. With enough data, scientists hope to finally determine what dark matter actually is. If dark matter particles exist, Euclid's maps, combined with laboratory detectors, might finally catch them. If modified gravity is correct, Euclid will reveal discrepancies in how lensing behaves compared to dark matter predictions. Either way, Euclid will push us toward answers. But Euclid isn't working alone. Another powerful telescope is coming, one that will push even deeper into cosmic history. The Nancy Grace Roman Space Telescope will launch around 2027. Named after NASA's first chief astronomer, Roman will complement Euclid's mission with even greater capabilities. Where Euclid maps wide areas, Roman will look deeper into specific regions. Roman's mirror is 7.9 feet across, nearly twice the width of Euclid's mirror. This means Roman can see fainter objects, more distant galaxies, further back in time. The telescope will peer into cosmic epochs when the universe was only a few billion years old. This is critical for understanding dark matter's role in structure formation. We can see galaxies today. We can observe relatively nearby galaxy clusters, but seeing how these structures formed requires looking at the early universe. Roman will provide this view. The telescope carries advanced instruments for measuring weak gravitational lensing. Its wide-field camera can photograph areas of sky equivalent to 100 times the area of the full moon in a single exposure. This efficiency allows Roman to survey enormous regions quickly. Roman will conduct a high-latitude wide-area survey. This project will observe about 2,000 square degrees of sky. It will photograph hundreds of millions of galaxies. Each galaxy's shape and distance will be measured. From this data, scientists will create three-dimensional dark matter maps, even more detailed than Euclid's. One of Roman's key missions is studying dark energy. That's the mysterious force causing the universe's expansion to accelerate. Dark energy is even more mysterious than dark matter. It makes up about 68% of the universe. Dark matter is 27%. Normal matter is just 5%. Understanding dark energy requires understanding dark matter. The two are connected through cosmic evolution. Dark matter creates structure through gravity. Dark energy pushes structure apart through cosmic expansion. The balance between these forces determines how the universe evolves. Roman will measure this balance precisely. It will observe type Ia supernovas at various distances. These exploding stars serve as cosmic measuring sticks. By comparing how bright they appear versus how bright they should be, scientists calculate how much the universe has expanded. This expansion history reveals dark energy's properties. It also constrains dark matter models. If dark matter doesn't behave as expected, the expansion history would be different. Roman's measurements will test these predictions. The telescope will also search for gravitational lensing by dark matter subhalos. Remember, dark matter might not be perfectly smooth. It might contain smaller clumps embedded within larger structures. These subhalos would create additional lensing effects. Roman might detect them. Finding subhalos would tell us about dark matter's particle properties. Different particles produce different subhalo populations. WIMPs create many small subhalos. Axions create fewer, larger ones. Primordial black holes create different patterns still. Roman's observations could distinguish between these possibilities. Roman will observe exoplanets too, not directly related to dark matter, but the same technology that detects weak lensing also detects planets around distant stars. Roman could discover thousands of new worlds while mapping invisible matter. The combination of Euclid and Roman will provide unprecedented data about the invisible universe. Two powerful telescopes working complementarily. Euclid mapping wide areas, Roman diving deep into specific regions. Together, they'll constrain dark matter models more tightly than ever before. By the early 2030s, we'll have detailed maps showing dark matter throughout cosmic history. We'll know how dark matter clumps, how it flows, how it evolved. We'll see which theoretical predictions match observations and which fail. This might finally solve the mystery, or it might deepen it. What if the data contradicts all existing theories? What if dark matter behaves in ways nobody predicted? That would be the most exciting outcome. It would mean the universe is stranger than we imagined. Scientists are ready for either possibility, discovery, or deeper mystery. Both push science forward, both expand human knowledge. The question is, are we ready to accept what the universe reveals? 85% of the universe is invisible to us. This fact should be humbling, terrifying even. Everything we've ever observed, every star, every planet, every human civilization, represents just 15% of reality. We're living in a cosmos where most of existence remains completely hidden. Some people find this depressing. It reminds us how limited our perception is, how little we actually understand, how our theories might be built on incomplete foundations. We pride ourselves on scientific knowledge, yet 85% of the universe escapes our comprehension. But here's a different perspective. This ignorance is our greatest opportunity. It means the biggest discoveries in human history are still ahead of us. The most profound truths remain uncovered. Future generations will unlock secrets we can't even imagine asking about. Think about the journey we've taken. 50 years ago, Vera Rubin noticed something strange about galaxy rotation. That simple observation opened up an entirely new field of research. It revealed that we were missing most of reality. One curious scientist asking a basic question uncovered one of the deepest mysteries in physics. Since then, thousands of scientists have worked to solve this mystery. They've built detectors underground. They've launched telescopes into space. They've smashed particles together at nearly light speed. They've developed new mathematics and new theories. Humanity has invested enormous resources trying to understand the invisible. We haven't found the answer yet. Every detector comes up empty. Every theory has problems. The mystery remains unsolved. But that doesn't mean we've failed. Failure is how science progresses. Every negative result eliminates possibilities. Every failed theory teaches us something new. We know dark matter isn't made of any particle we've discovered so far. We know it doesn't interact strongly with normal matter. We know modified gravity doesn't fully explain observations. These negative results are valuable. They constrain what dark matter could be. The search continues. New experiments are starting. Bigger detectors, more sensitive instruments, novel techniques nobody has tried before. Scientists are exploring theories that sound like science fiction. Extra dimensions, hidden sectors, exotic quantum fields. Some of these ideas will be wrong, but one might be right. And when we finally solve this mystery, when we understand what dark matter actually is, it will change everything. It might revolutionize physics. It might enable new technologies. It might reveal that reality is far stranger than we imagined. The discovery could be this century's equivalent of quantum mechanics or relativity. But even if we don't solve it in our lifetime, the search itself has value. The experiments we build push technological boundaries. The theories we develop expand our mathematical tools. The observations we make reveal details about cosmic structure we never knew existed. Science advances through the journey, not just the destination. Young people entering science today have an incredible opportunity. They can work on one of the deepest unsolved problems in physics. They can explore unknown territory. They can discover something that will echo through history. The person who figures out dark matter will be remembered forever. Their name will sit alongside Newton, Einstein, and Rubin. But it's not about fame. It's about understanding. Humans are curious creatures. We need to know how the universe works. We're bothered by mysteries. We can't rest until we've figured things out. That drive to understand is what makes us human. Dark matter reminds us that we're still explorers. We're still pioneers. We haven't figured everything out. There's still room for radical new discoveries. The universe still has secrets, and we're determined to uncover them. Some mysteries stay mysterious for centuries. Others get solved quickly once the right technology or idea appears. We don't know which category dark matter falls into. Maybe someone already had the key insight, but we haven't recognized it yet. Maybe we're one clever experiment away from the answer. Maybe it will take another 100 years. Either way, the search continues. Scientists will keep building detectors, launching telescopes, developing theories, testing predictions, making observations, analyzing data. Each generation pushing a little further than the last. Each discovery revealing one more piece of the cosmic puzzle. You're living through this, right now. This moment in history, when humanity is grappling with the realization that most of reality is hidden from us. Future humans will look back at this era. They'll study how we searched for dark matter, how we struggled with the mystery, how we eventually solved it. 50 years from now, this video will be a historical document. People will watch it to understand what we knew and didn't know in 2025. They'll see how close or how far we were from the truth. They'll be amazed by what we missed or impressed by what we figured out. The universe is vast. It's mysterious. It's mostly invisible, but it's knowable. Piece by piece, observation by observation, we're uncovering its secrets. We're building a picture of reality that includes things our ancestors never imagined. So yes, 85% of the universe is invisible. That doesn't make us insignificant. It makes us explorers standing at the edge of the greatest frontier in human history. The darkness isn't empty. It's full of answers waiting to be discovered. And that's not depressing. That's thrilling. That's why we do science. That's why we keep searching. Because somewhere in that invisible 85% lies the truth, and we're going to find it.